Welcome to our presentation titled The Temperature Evolution Inside Liquid Foods of Different Viscosity During Reciprocal Agitated Processing in the Shaka Retort. My name is Davy Verheyen and I will present our work today, which was a collaboration between KU Leuven, Nofima and Ankara University. Here you can see the structure of our presentation, starting off with the introduction. You can here see a collection of different food products. What they all have in common is that they can be treated with thermal treatments, which is of course the subject of our work today. Now, what do we not want to happen when we have such food products? That there are microorganisms, foodborne pathogens, for example, bacteria, present inside or on the products, because when this happens, people might get sick. In bad cases, they might even be hospitalized, and in the worst cases, people might die, which of course we don't want to happen. Here then a few examples to illustrate that this is still a common issue. Now the message to take home here is that the left and right examples are of foodborne illnesses caused by products which were not heat treated. So here on the left, enoki mushroom, which caused Listeria outbreak, and here on the right, a seafood salad which was contaminated with E. coli, both causing hospitalizations and Listeria outbreak, even causing a few deaths. Now the middle example is an outbreak associated to pasteurized chocolate milk, so heat treated, and this shows that even in this case we could still get the problems with food safety. Now to illustrate this, an example of a typical food chain, the processing plant, transport and storage, and consumption at home. And here at the bottom you see in blue the cell numbers inside the food product, and in green the temperature to which the food products are exposed. Now, if you start in the food processing plant here, there might be in the beginning a certain number of foodborne pathogens present inside the food product. Here they might give it a thermal treatment which kills off a large amount of the bacteria or microorganisms. Then they try to keep the temperature low during transportation, during storage, and when at home you of course try to do the same in your fridge. And then when the people want to eat their food, they might heat it again by baking or frying, and then this kills off a lot of bacteria again and gives us a safe food to consume. We were mainly interested in this step here, the microbial inactivation and the processing plant. A typical way to accomplish this is retort heating. So I've included a small schematic of this in here. Here inside the basket of the retorts, people place their food products, could be in cans, pouches or bags, whatever. And then the rest is actually just a way to heat water or cool water to heat or cool the products. Similar things could be achieved by steam, which is directly injected. Then a bit of history to show here. I won't go too much into detail about this, but the most interesting thing is to see that in 1852 the first heating retort was invented. In 1920 there was an important improvement of the process where they started to agitate the cans or pouches inside the retort, and so this is where we are today, 2020, and you can see that this development was only 100 years. It was already 100 years ago, so quite a while ago. Agitated retorts, the most typical thing they do there is rotation. So this induces forced convection inside the products, which improves heat transfer and also reduces processing times. The two most typical examples are end-over-end rotation, first of all, in which the rotational axis, well, the rotational plane is along the symmetrical axis of the cans. The other one is actual rotation, where the rotational plane is perpendicular to the symmetrical axis of the cans. And here the most typical way to do this is just rolling the cans inside the retort while the food is heated. Then what happened only a bit more than 10 years ago, they invented something new, which is the Shaka retort. What is that? Here a typical example of such retort, actually the one we used for our study. Here you see how it works. So here we have actually reciprocation as an agitation, and the cans are moved horizontally back and forth, mainly with agitation rates between 1 and 5 Hertz. The advantage here is that it can be used for liquid foods over a broad viscosity range, even with particulates inside, and that compared to the other agitational rotational processes, this improves heat transfer and in turn reduces processing times, giving it better food safety and food quality compared to the more traditional methods. And this is mainly related to the fact that it's quite a novel technology, is that we don't know a lot about it yet because of that. And one of those things that we don't know yet what is the influence of food microstructure on the process. Moving on then, in relation to this, to the objectives of our study. So if we assume that this here is a typical can or pouch with our food product inside, we want to know the temperature distribution during the Shaka process, and this over time, but also over location. As you can see, did we want to achieve this? So we combined experiments in a real Shaka retort with simulations in using ANSYS Fluent. For this we used different food-like systems, well, some of them at least. So we used food model systems, artificial food model systems based on fish products. And we compared this with a simple distilled water case, for which we actually in this study did the simulations, because that's much more simple than the more complex food model systems with fat, protein, salt, and a certain relatively high viscosity. And what we wanted to achieve is we wanted to know what the effect of food microstructure is during the heating process, and actually also when you inactivate bacteria. Moving on to the materials and methods. So here a picture of the used Shaka retort with its specifications. This is the typical, well, this is the process that we used. So it's actually consists of 4 phases, and in red is shown the retort water temperature. First, we have a heating phase, short with 80 strokes per minute agitation. Then we hold the product at 70 degrees more or less for almost 9 minutes, shaking of 100 strokes per minute. And then we have 2 cooling phases, actually with different shaking rates to achieve in the end 20 degrees. And this enables us to open safely the retort and take out the samples again. Here are the different model systems that we used. So as I said, they are fish-based model systems. We developed them in a previous study. And out of interest now, actually, in this part of the work is the low viscosity liquids, which I will henceforth address as liquid, and high viscosity liquid, which I will call xanthan, because the high viscosity is achieved by addition of xanthan gum. And then the simple distilled water case. The 2 emulsions with 10 and 20% fat were not included in the focus of this work, but they are more important for the future work, which will follow. These are the beakers that we used, height of more or less 7 centimeters. You can see the other dimensions on the picture. We filled them up to 90% to have a 10% headspace inside the beaker. This is mainly to enable the liquid to mix during shaking. And this is the position of the mini loggers we used for temperature measurements. And you see here again the specifications of those. And this is 2 pictures of how we attached the different beakers inside the Shaka retort. Here you see the computational geometry, which was used for the simulation. So almost 400,000 nodes were used for this, and for the fluid inside, the continuity, momentum, and energy equations were then solved simultaneously to simulate the behavior of the liquids during reciprocation, and also the heat transfer, of course. And then the results and discussion. So here we see the temperature evolution inside the different systems. So we have the retort water, the simple distilled water, the liquid, low viscosity, and the xanthan, high viscosity. We see that the distilled water is quite similar to the low viscosity liquid, for small differences, but for the xanthan gum, the xanthan system, there was quite slower heat transfer, as we can see here. So here we clearly see the influence of viscosity on the temperature evolution inside the different systems. These are then the results for the temperature simulation in the distilled water case. We see in blue and orange the two experiments inside the Shaka retort, and then in yellow the simulations. So actually they're quite accurate up until now, which is of course good. Proves the use of the simulation results. Then here is a snapshot we took of the temperature distribution after 90 seconds. Quite homogeneous at this point. Temperatures between let's say 30 and over here 40 degrees, maybe a bit more at the edges, of course. If you move 180 seconds a bit further into the process, then actually temperature gets more homogeneous, around 50 degrees, which is good, of course, which is what we want. And then here the volume average temperature change. We see here the same temperatures I mentioned before at 90 and 180 seconds. And this is, here you can see in red the water phase, and in blue the air, which is, shows the phase field movement. So here we see a snapshot at 90 seconds. More interesting at 180 seconds, because here you actually see some mixing of the air bubble with the water phase, and this also of course improves the heat transfer. Then to conclude, first of all, we saw that the temperature evolution was dependent on product viscosity. This is the graph I showed before. And secondly, we saw from the simulations in the distilled water that we were able to achieve a homogeneous temperature distribution inside this water. It's of course positive. Finally, the future work which we're planning. So here again, the model systems that we used. So in the future, we would also want to do, of course, the simulations in the other model systems. We are working on that as we speak. And also in the two emulsion systems. And this will give us an idea of what the influence of this food macrostructure now actually is. Something to illustrate this, these are results which are now submitted to a journal, Food and Bioproducts Processing. Here we see Listeria inactivation in the different model systems, which I showed before. So in blue, always the temperature evolution, in black, the modeled inactivation of Listeria based on these crosses here, which are sampling points. Yeah, we see, first of all, that the temperature increase in the xanthan and the emulsion systems was much slower, well, relatively slower than in the simple low viscosity liquid, which of course also has as a consequence that the inactivation is slower, as we see. But among those three systems, the temperature profiles, average temperature profiles, I should stress this, are quite similar. And that's where it gets interesting, because the inactivation is not. In emulsion 20 there's almost no inactivation, the other there is quite some, but yeah, we see those differences. And what we would want to achieve with the simulations in all the systems is see how is the temperature distributed, and this way we can then decide whether those differences are either caused by heterogeneous temperature profiles. Are there some cold spots in which there is no inactivation or very limited inactivation? Or if this is not the case, if there is like some effect of the microstructure directly on the cells, for example, between these two, is there an effect of an increasing fat content? So we believe that the computer simulations really help us in shedding some more clarity on this, which we hope to see in the future, of course. Then I'd like to show you some acknowledgements and some contact information. So if you want more information about our research, we can contact the following people. Also see the Twitter address, our website, and I'd like to acknowledge again the three partners which have worked on this research, being BioTeC Plus, Nofima, and Ankara University. And then the only thing that's left is to thank you for watching this presentation.